Let's get started again. Welcome back. This is now the 20th lecture of the condensed matter course. When we last left off, we were talking about magnetism, and we were thinking about magnetism one atom at a time. And in this lecture, we're going to sort of upgrade and start thinking about collective magnetism. In other words, magnetism when we have lots of atoms. Collective magnetism, using the theme that more is different. When you put lots of things together, you can get new and different physics. Now, we did start a little bit of collective magnetism last time when we were talking about Hund's rules. When we talked about Hund's rules in a molecule, there was the driving force by Hund's rule to try to align spins between atoms in a molecule, but there was also the covalent bonding physics, which tried to anti-align spins so you could make a singlet or covalent bond. And those two things compete with each other. And getting the details right to figure out whether the spins will align or anti-align is sort of a complicated process, and we're going to brush that entirely under the rug and try to take a step back and look at a model that's going to sort of give us much of the physics that we're interested in without getting too bogged down in the details. So we have a couple of approximations in our model. So our toy model will have one, no electron hopping. So we don't have to worry about any sort of band physics. We don't have to worry about tight binding model. We don't have to worry about polyparamagnetism. All of that has been thrown out. So with no electron hopping, we can assume that on each atom there is a spin Si on each atom on atom I. And I put spin in quotes because this spin, what I really mean is a magnetic moment. That magnetic moment may be from an actual electron spin. It may be from many electron spins. It may be orbital angular momentum. It may be some combination of orbital and spin and angular momentum. But generally, when you sort of make these sort of toy models, you just call it spin no matter what it's actually from. And then we'll write down the Hamiltonian. So here's a Hamiltonian, 3. H equals, and then it has two pieces. The first piece should look familiar. G mu b b dot Si. That's just the coupling of the spin to the external magnetic field. This is the term that gave us paramagnetism. Then we're going to add to it another term, sum over, oops, I'm going to put a minus sign and a 1/2 out front, sum I and j over atoms I comma j of j ij si dot sj. So this term here is an interaction term. So j ij is the interaction between atom I and j, between atoms I and j. And we will set jij equal to jji. And this is also sometimes called, also equals, known as exchange, the exchange constant. This is how the word exchange is used in condensed matter physics most of the time. And the factor of 1/2 is put in there to prevent overcounting. We want J1, 2 to be the interaction between atom 1 and 2. But in that sum, there will be a term S1 dot S2 and another term which is S2 dot S1. We don't want to overcount them, so we just put a 1/2 out front. Okay? So this model, model 3, the Hamiltonian 3 is known as, so 3 meaning the Hamiltonian 3, is known as the Heisenberg model, after everyone's favorite uncertain physicist, Heisenberg model. Very frequently studied model in condensed matter physics and a very good representation of many magnets. Now we're going to simplify this even further, by setting jij equal to j if I and j are neighbors, ij neighbors. And we're going to set it equal to 0 otherwise. In other words, we're just going to keep track of interaction between spins that happen to be nearest neighbors with each other. It's a fairly good approximation that spins on atoms that are close to each other see each other, and if they're farther from each other, they don't see each other. And then we're also going to simplify, so this is simplification 1. And simplification 2 is, for now, we're going to set the external magnetic field to 0, and we may put it back in later. So our Hamiltonian now takes the form H is minus 1/2 sum over ij, and I'll write like this. So this notation means I and j are neighbors. Bracket notation, sort of standard. J si dot sj. So we're only summing over I and j being neighbors, and the constant is just a constant j here. Now there's a couple possibilities of what you can get out of this sort of Hamiltonian. So possibility one, so let's write down case one. Case one is that j is greater than 0, in which case, in order to make the energy of that Hamiltonian as small as possible, the two spins on adjacent sites will try to align with each other. So spins align. And when the spins align, what you get is ferromagnetism. Magnetism. Magnetization, which is not equal to 0. Now, it doesn't matter in this Hamiltonian which direction the spins all align in, as long as the spins are all aligned with each other. So they can all be pointing up, they can all be pointing down, they can all be pointing to the left, they can all be pointing to the right. Same, you'll end up with the same energy. What's important is all the spins align with each other, okay? So this is the easy case to study. The more complicated case to study is case 2, is j less than 0. Now with j less than 0, the neighbors want to anti-align in order to make the Hamiltonian as small as possible, or the energy as small as possible. So then what we have is, if we have let's see, right down here. So if we have like a square lattice like this, each with a spin on it, if the first spin is pointing up, then the second spin will want to point down in order to make the energy as small as possible, and then the third spin will point up, this one will point down, this one will point up, this one will point down, so forth and so on. And we'll get these alternating spin structures. This is what's known as an antiferromagnet. Or sometimes known as a Néel state, N-E-E-L, Néel state, after Louis Néel, who realized that these things actually exist in nature. And then what's interesting about these is that they have magnetic order, but they have no net magnetization, M equals 0. Why they have no net magnetization? Well, because you have the same number of up-pointing spins as you have down-pointing spins. Well, at least if I drew them more aligned, it would look like there was an equal number of up-pointing spins as down-pointing spins. My drawing isn't so good. So how is it that Louis Néel knew that this sort of situation could occur? Well, on one of the homework assignments, the last homework assignment, you're meant to calculate the magnetic susceptibility of a state like this, and there's actually some signature in the magnetic susceptibility that you can look for, which was the thing that Néel was looking at, and what made him realize that these antiferromagnetic states actually exist. But in the modern era, there's actually a very direct way to see this sort of physics, which is to do neutron scattering on it. So let me make sure you can write that down. You can see with neutron scattering, or neutron diffraction, I guess we should call it. So the elementary lattice constant here might be A, but the neutrons actually see a lattice constant which is this big. This is the unit cell now, because the neutrons, if a neutron is coming in with spin up, it sees an upspin as being a different atom from a downspin. And the reason that neutrons see an upspin as being different from a downspin is the neutrons themselves have spin, and they interact differently with, if the neutron coming in is a spin up atom, it will interact differently with this atom than with this atom because their spins are anti-aligned. So it sees a unit cell which is this big, A prime. So when you do your neutron diffraction experiment, you will see a different size of the unit cell when antiferromagnetism occurs. You get a bigger unit cell. I should actually comment one more thing here, which is a little subtle, but there's a homework assignment on it as well. That in this picture, I've drawn, or I should have drawn if I was a better artist, up spins, down spins, up spin, down spin, up spin, down spin. And that's a very classical way of thinking. I'm thinking of these spins as actually being vectors that you can point in any direction in space. If you have large spins in the sense of spin 5 halves, or spin s equals 2, or s equals 9 halves, or s equals 3 or 4, or something like that, then having this picture in your head of these spins as just being vectors that can point any direction in space is a fairly good classical picture, which is fairly accurate. But if you're talking about spin 1 halves, then it's not so good anymore. You really have to think in terms of quantum mechanics, and you can't draw these pictures of upspin, downspin, upspin, downspin. And spin 1 half antiferromagnet is a very complicated beast, and it's not really right to think of it this way. This is sort of more of a classical intuition that works for large spins, but not so well for small spins. And that will be presumably worked out in a homework assignment. All right. So one more comment about this case of antiferromagnetism is that you can have antiferromagnetic coupling, ferromag, on a triangular lattice, and then you'll get something really strange. Triangular lattice. So let's imagine we have a triangle here, 3 atoms in triangle. And if the first one happens to have his spin up, the second one up here wants to have a spin pointing in the opposite direction from this one, so he points spin down. And then this one wants to have an opposite pointing spin to each of his neighbors, but he's in trouble. He can point up and then make the opposite direction of this guy, but the same direction as this guy, or he can point down, in which case he's opposite this guy, but same direction as this guy. So this guy's in trouble, and he can't point happily either direction. So this is what you call a frustrated antiferromagnet. Everything causes frustration these days. Okay, so one more case of this antiferromagnetism, or similar physics to antiferromagnetism, that I want to mention is the possibility that you have a basis, or let's consider a 2-atom basis, or two or more atom basis for a lattice, for a crystal. So let's consider, for example, a big atom, a small atom, a big atom, a small atom, a big atom, big atom, small atom, big atom, small, big, something like this. So here's a 2-atom basis. Okay, now imagine that we have antiferromagnetic coupling where the neighboring atoms want to point their spins in opposite directions. So the big atom, say, points up, then the small atom points down, big atom points up, small atom points down, big atom points up. Okay, we can keep going here. You get the idea. And, okay, up, down, up, down, up. If the spin on the big atom is not equal to the spin on the small atom, then what we'll have is we'll have magnetization not equal to 0, because you'll have more magnetization pointing up than you have magnetization pointing down. Is that clear how that works? So even though you have antiferromagnetic coupling and each neighboring spin wants to point in an opposite direction, you get a net magnetization left over because some of the spins are bigger than the other spins. And this is what is known as ferrimagnetism. Ferrimagnetism. And it may seem like it's kind of strange or unusual, but it's actually quite common. In fact, the world's most common magnet occurring in nature, it's iron 3 oxide 4, otherwise known as magnetite or lodestone, that you can find in the earth sometimes, and it's magnetized when you pull it out of the earth, and it will stick to your refrigerator directly, is actually a ferrimagnet. It's made up of more than one type of atom, larger moments on one type of atom, smaller moments on the other, and they anti-align with each other. Then there's an argument in the community as to whether you should call a ferrimagnet a subset of a ferromagnet. And this is where people will argue with each other till they're blue in the face, and there's no actual good answer to this because people use it both ways. So some people say that a ferrimagnet is a subset of a ferromagnet because it has non-zero magnetization. It will stick to your refrigerator. It has the property that we think of as a magnet. On the other hand, some people think that the word ferromagnet should be reserved for the case where all the spins point in the same direction, and we should call this a ferrimagnet to distinguish it from the case where all the spins are pointing in the same direction. So anyway, you should just be aware that there's that little conflict of nomenclature in the community. Okay, so far so good? We're doing well still? All right. So let's move on to, actually, maybe, I'll write it again. We'll write down the Heisenberg Hamiltonian, H Heisenberg. Again, minus 1/2 sum over neighbors ij of j si dot sj. And as I mentioned, and we're going to sort of focus mostly on j greater than 0, in other words, the ferromagnetic case. And as I mentioned, this Hamiltonian doesn't care which direction the spins point as long as they're all pointing in the same direction. Now, unfortunately, most materials aren't like that. Most materials actually prefer the spins to point in some particular direction. And so this is, in order to represent that, we need to add another term to the Hamiltonian. And actually, first, this is something I mentioned in the last lecture, but I'll mention it again. One thing that would make it obvious that the directions aren't all equivalent is if you imagine having a very long tetragonal unit cell where the crystal is very long and thin in one direction, then you might imagine that maybe the spins want to point along the long thin axes, maybe. So you might have S wanting to be up or S wanting to be down, but not any direction in between. So this is sort of a case where you might expect this sort of anisotropy to exist. So in order to represent that, we write down an additional term of the Hamiltonian, dH anisotropy, or H anisotropy. I would call it D, I'm not sure. Which might take the form sum over all atoms. Let's put a minus a kappa out front. That's some constant. Si in the z direction squared. So why is this going to prefer having the spin in some particular direction? Well, it wants to maximize the magnitude of Sz. So if Sc is pointing in the direct up direction or the direct down direction, this Hamiltonian is as small as possible. It gets as negative as you possibly can as compared to having S point in the, on the S equals 0 plane, where this gets less negative. So this kind of term, this anisotropy term, is one we're going to consider a lot. So maybe I'll even write down likes to have S up or S down, not S pointing sideways. Now, for a cubic crystal, you might expect something dH cubic, which is a little more complicated, that would allow the spin to point along any of the crystalline axes, but not in between the crystalline axes. And an appropriate Hamiltonian for that might be something like this: SIX to the fourth plus SIY to the fourth plus SIZ to the fourth. And the reason I wrote this to the fourth power is because if I wrote them to the squared power, then you just get sx squared plus sy squared plus sz squared, which is just s squared, and that doesn't care which direction the spin is pointing because it's just the magnitude of the spin. But if you write it as fourths, sx to the fourth, sy to the fourth, sz to the fourth, then this prefers to have the spin pointing along one of the crystalline axes, but not in between the crystalline axes. So we might consider this one a little bit as well, but mainly we're going to focus on this one. Just one comment. Again, for small, what we've written here is sort of based on our intuition for spins when we're thinking of them as classical vectors. For small spins, these can be trivial. These terms can be trivial. What do I mean by that? Well, suppose I tried to write this down for a spin 1/2. Remember this spin 1/2 Pauli operator, sigma z, the Pauli spin matrix. If you square it for spin 1/2, the spin matrix sigma z squared is just 1. It's a very uninteresting operator. It just gives you a constant. So if you tried to write down a term like this for a spin 1/2 spin, it would do nothing. It wouldn't specify which direction the spin wants to point in. However, if you did it for a spin 2 or spin 3, there would be an analogous spin matrix which does not square to 1 and becomes non-trivial. So that's just something to be warned about. You can't write down anisotropy terms for small enough spins. Okay? All right. So we need to think about this anisotropy, which will prefer the spins to point in some directions over other directions. And we need to think about two possibilities. One possibility is that the anisotropy is strong, and the other possibility is that the anisotropy is weak. So maybe I'll write down the weak case over here. Weak anisotropy, by which I mean that this kappa, this coefficient that occurs in the anisotropy term, is much less than the J, the exchange constant that occurs in the Heisenberg term. Now, in this case, what one has to do is one has to first, or most importantly, first use spins aligned with neighbors. Spins aligned with neighbors. And why I say that first, I mean it's most important to align with your neighbors because J is the big energy scale in the system. Once you've aligned with your neighbors, second, you align with anisotropy axis. So first, you align with your neighbors, and then everyone decides that they're better off if they all align with the anisotropy axis. Now, if you compare that to the case over here, strong anisotropy, meaning this kappa, this anisotropy constant, kappa is much bigger than J, then first you want to align along anisotropy axis. Align along anisotropy. For example, all spins will point either up or down if we're using that up and down anisotropy. That everyone has to point either up or down. That's what you do first, because that's the big energy scale in the system. But then second, you align with neighbors. Align with neighbors. Now, this may seem like it's a trivial distinction, because at the end of the day, the ground state is the same. The ground state is that everyone's aligned with their neighbors and everyone's aligned along the anisotropy axis. So why did I make a big deal about this? Well, it makes a difference. The two limits are different if you think about what the low energy excitations are. So in this case, the low energy excitations are small angular rotations of a whole bunch of spins. Everyone stays more or less aligned with their neighbors, but they rotate just a little bit from the anisotropy axis. So this is small rotations. Small rotations staying aligned with neighbors. Whereas over here, the low energy excitations are completely different. Low energy excitations here, the thing that's important is that you have to stay aligned with the anisotropy axis. So the low energy excitation is to flip some spin, but keep it aligned with the anisotropy axis, but stay aligned, but stay on anisotropy axis. Okay, is it clear what the difference is between these two? Okay, so this is an interesting case here, and it's sufficiently interesting that people study it a lot, and they write down an effective model for this one. Model, which has the following properties. We write some sigma I, which is plus or minus s, the magnitude of the spin, and then si is, as a vector, is sigma I in the z hat direction. So basically, we're only letting the spin have complete magnitude pointing exactly up or full magnitude pointing exactly down. And then we can write out our Hamiltonian, very similar to the Heisenberg form. Heisenberg form, H equals, okay, so there'll be minus 1/2 sum over I and j neighbors, j sigma I, sigma j, and then plus, we'll couple it to the external field, G mu b, b sigma I. This Hamiltonian is known as the Ising model, because it was invented by Lenz, not Ising. Ising was the graduate student who Lenz gave this to as a project in 1925, and he solved this for his PhD project in one-dimensional case. Now, I'm going to make a big deal about this Ising model because this Ising model, it's extremely simple, and yet it's also extremely complex. It's simple because on each site, there's only one degree of freedom. Either it points up or it points down. There's no other possibilities. So it's very simple degrees of freedom. And it couples only to its neighbor, and yet the physics of this model are extremely complex. And it's probably not an exaggeration to say the world has learned more about statistical mechanics from this one model than from anything else we've possibly studied. So Ising solved this model in 1925 in one dimension. During World War II, Onsager very famously managed to solve it without magnetic field in 2 dimensions. No one has solved the model either in 2 dimensions with a magnetic field or in 3 dimensions or any higher dimension since then. So it's been a lot of study. Thousands and thousands of papers have been written about this model since then. And I should mention, just in the last few years, there's been a really valiant assault against solving this model in 3 dimensions, and maybe within a few years there will be a solution, maybe not. We can be optimistic. But the reason that this model is so interesting is because it shows an awful lot of interesting physics, particularly about phase transitions, even in this model that only has 1 degree of freedom on each site. Okay, so we'll come back to the Ising model actually in the next lecture, and then we will ask the question, where am I going to put it? Here. No, let's put it over here. Okay, for any model that we write down, so we're starting here, if we have a Hamiltonian, which is h of the Heisenberg form plus the anisotropy form, and if the anisotropy is strong, we can just replace the combination with the Ising Hamiltonian. Does the whole system align? The system align at t equals 0? And in the model, the answer is yes. In the model, yes. But in real magnets, no. So in real magnets, not all the spins in the system actually do align with each other. And to understand why this is, we have to realize that we actually left something important out of our Hamiltonian. So let's do a little bit of a Gedanken experiment. Let's imagine you have a big chunk of some magnetic material, another big chunk of some magnetic material. This one has a magnetization here, this one has a magnetization here. Then you bring these 2 chunks of materials together. Well, what happens? Well, you've probably done this when you were a kid at some point, and when you bring them together, you realize that they want to sit like this. They want to sit head to tail because they have a dipolar interaction, and so the magnets want to come together head to tail, and they really don't want to come together head to head like this. So this is telling us that we left out some important piece of physics, and what we left out magnetic energy. Magnetic energy, that's one way of thinking about it, or dipole-dipole interaction. In the last lecture, I mentioned that if you're thinking about 2 spins in a given atom and asking whether they want to align or not, the dipole-dipole interaction between 2 spins in an atom is insanely small, so you could ignore it. That's true, but if you have a big chunk of a material, you have an insanely large number of electrons there, each with an insanely small amount of dipole moment, and you put them all together, it actually becomes a reasonably big dipole moment, and you do have to worry about this dipole-dipole energy. Another way of thinking about it, exactly the same physics, is to, if you think about the magnetic field lines in these 2 pictures here, magnetic field lines look kind of like this in this picture, whereas in this picture, the magnetic field lines kind of look like this. And you remember that the magnetic energy, total magnetic energy, is integral d3r of b squared over 2 mu naught. And just the total b squared is a lot smaller if you align your dipoles head to tail. So you're reducing magnetic energy by putting your dipoles head to tail in this way. So what actually happens in a real physical system? So we're going to now write H equals H Heisenberg plus H anisotropy, plus we're going to add H dipolar interaction or magnetic interaction, magnetic energy. Then what actually happens is you get, here's your big system. The system will break up into what are known as domains, sometimes called Weiss domains, where some point up, some point down, some point up, like this. It'll break up into many little domains. Now what's going on here, at some point in this material, you'll have upspins right next to downspins. And that makes the Heisenberg term of the Hamiltonian very unhappy, because the Heisenberg term of the Hamiltonian wants the upspins to be next to upspins. So there's some energy cost along that, that transition, along that what's known as a domain wall. Maybe I'll even write that down. This is the transition is called a domain wall between the two. So there's some Heisenberg energy to have upspins next to downspins on the domain wall. But you sacrifice that Heisenberg energy in the domain wall in order to save magnetic energy or dipolar energy for the whole system as a whole. Okay? If you had a different type of anisotropy, so for example, cubic anisotropy, the domain wall structure might look different. You might have something that looks like this, where this points up, this points right, this points left, down like that. And this is putting each dipole sort of head to tail with the next dipole. That improves the energy even better. Now, what happens in this case is that overall, the total magnetization of one of these magnets is now 0 again, because you have just as many up domains as you have down domains, and you get no magnetization at all. And then you might, scratch your head and say, well, wait a second, I know magnets exist, and, so how is it we're going to get magnetization out of our magnets? And so now we have to start thinking a little bit carefully. The first thing we can do, and actually I guess I have a slide better than drawing bad pictures again. The first thing you can do is you can imagine if you add a magnetic field externally to the system, the size of the domains will re-equilibrate. And if the magnetic field that you apply is pointing up, you'll get more up domains than down domains, and you'll get a net magnetization again. But still, if you take away the magnetic field, the domains move back to their old equilibrium over here, and you'll have no magnetization. So this thing that we thought was supposed to be a ferromagnet is in fact a paramagnet, and it can be a very good paramagnet, which gives you a very high magnetization for a very small magnetic field, but it's still, unfortunately, a paramagnet. So how are we going to get this thing to be magnetic even in the absence of an applied magnetic field? So the whole trick to making a real magnet, the kind of thing that sticks to your refrigerator, is to find a way to prevent the domains from going back from this configuration to this configuration. So you, quote, train a magnet in a high magnetic field so it gets to one of these configurations where there's more upspins than downspins, or up moments than down moments in this picture. But then you find a way to prevent the domains from moving back. This is what's called pinning of domain walls. Pinning domain walls. And the way you typically pin a domain wall is with disorder. And whether one is trying to design a magnet for use in electrical motors, whether you're trying to make a magnet that will stick to your refrigerator, whether you're trying to make a magnet for a magnetic disk drive, the whole art to making good magnets is to figure out how to make the disorder prevent the magnetic domains from moving back to their original configuration where the magnetization goes back to 0. Okay, so why is it that disorder is going to help you? All right, so here's the picture that's supposed to show us here. So this is an Ising. Did I mention the whole business about Ising versus Ising? I didn't say that, did I? Did I say that? Okay, so let me tell you. So Ising was German, and apparently the way it's pronounced is Ising in Germany, I believe. But then after he finished his dissertation, he went to the United States, and people called him Ising for the rest of his life. And so everyone in the United States calls it the Ising model. Everyone in Europe calls it the Ising model. I'll probably never get it straight, but I think it is correct to call it Ising Anyway, so this is an Ising magnet. All the spins are pointing either up or down. And the interaction between spins is unhappy along the domain wall. And I've drawn all the unhappy spins in red here, where the up spins meet the down spins. Okay? And if you count them from top to bottom, there are 12 of these red bonds where there's an unhappy connection. Now, in this picture, there's a little green atom there, which is supposed to be a defect, someplace where there's no spin at all. If you happen to move over the domain wall to a different position over here so that it goes through the defect, there's only 10 red bonds now, not 12. So the energy actually drops if the domain wall goes through the defect. It's a lower energy for domain walls to go through defects, so they want to stick on the defects. And that's how you pin a domain wall with some disorder. By putting defects in the system, once the domain walls are in this configuration, you take away the magnetic field, but then they can't move back because they would have to give up some energy to move back to their original position because they're stuck on the defects. Okay? That's the general physics of how it is you make a real magnet which has m not equal to 0. So far, so good? Okay. So since the fundamental physics is really all wrapped up in the physics of the domain wall and how the domain wall moves, it's worth thinking about the domain wall a little bit more carefully. And it turns out that most magnets in nature are not of the Ising type, where the anisotropy is strong, but they're of this type, where the anisotropy is quite weak. So we have to sort of think about what happens for domain walls not in the Ising limit, but in the weak anisotropy limit. Over here, there's no question of what a domain wall looks like. For the Ising limit, you just have up spins, and then they meet down spins, and nothing interesting happens in between. But over here, where we have weak anisotropy, if you have up spins over here, and you have down spins way over here, remember that the most important thing to do for this weak anisotropy limit is to keep everyone as aligned as possible with their neighbor. So the way you get from upspin to downspin is to just slightly rotate each spin just a little bit from his neighbor and eventually make it from pointing up to pointing down with a slow rotation. Okay? And this is what's known as, let's say this goes over n spins. Okay, I didn't draw that very well, but you get the idea. And this is what's known as a block wall or a Néel wall, after Felix Bloch, the same Bloch's theorem guy, and Louis Néel, the guy who realized that we should have antiferromagnets. So let's try to calculate the energy and the width of this block. Okay, there is a slight difference between a block wall and a Néel wall. It depends on whether the rotation of the spin is in the plane of these atoms or it's transverse to the plane of the atoms. It's a detail that you probably don't have to worry about, but there's a slight difference between the two. At any rate, I think what I've drawn here is actually a block wall. So let's try to calculate the energy of this. So the energy in this one-dimensional picture is going to be sum over I guess, minus j si dot si plus 1. And here you might think that I've left out a factor of 1/2, but I haven't, because here, since I'm summing over I only in one dimension, S1, S2 only occurs in one term now. Okay, so I got the factor of 1/2 right. And if I align all the spins, E aligned, I then get sum over I guess I equals 1 to n of minus j s squared. Everyone is aligned with each other. And if I twist it, E twist minus E aligned, I'm then going to, let's call that delta E, equals delta E, the amount of energy you pay to twist the spin from top to bottom. That will be sum over I equals 1 to n of j s squared times 1 minus cosine of theta I. So for each time you twist the spin a little bit, you have to pay this sort of cosine energy. Theta I is okay, so that's theta I, the rotation of the spin from one step to the next. So let's assume that the theta is small, and if we need to get from all the way to the left to all the way to right in n spins, let's just declare all the thetas to be pi over n. So we have to make a pi rotation in n steps. So we'll say theta is pi over n. So cosine theta is then approximately 1 minus 1/2 pi over n squared. If I plug that into here, I'll get a total of n spins I'm summing over. I have js squared and 1/2 pi over n squared. Multiply that out. I then get pi squared over 2 js squared over n. And unsurprisingly, this tells me that the energy is lower if I rotate the spins more smoothly, that each spin wants to be as aligned as possible with his neighbor. And so if we were only considering this part of the Hamiltonian, the spins would, if they rotated, they would rotate infinitely slowly, and they would be most happy that way. But this has to compete with the anisotropy energy. Anisotropy, which wants the spins to be either pointing directly up or directly down. And so we have to estimate how much energy you're going to pay to have n spins in this wall, which are neither up nor down. And okay, this is a rather crude approximation, but we'll just say that each spin that's not pointing up and down, you pay an energy ks squared. Okay, I mean, this number is probably off by a factor of 2 or pi or something like that, but at least it will give us the order of magnitude correctly. So the total energy of the block wall, E total, is the sum of the Heisenberg energy, pi squared over 2 j s squared over n, plus the anisotropy energy, n kappa s squared. And then we have to minimize this, dE total dN, set that equal to 0. And that gives us, just differentiate that, we just get n equals square root of pi squared over 2 j over kappa. And so not surprisingly, what this is telling us is that if the anisotropy is extremely small, then and the Heisenberg coupling is extremely strong, then the spins rotate extremely slowly. Whereas if you're in the other limit, where the anisotropy is large and the Heisenberg coupling is small, then the spins rotate in a very small number n, maybe even directly from up to down in one step. Now, in real magnets, it's very often the case, you can have a case where n is greater than or about equal to 100 atoms. So you can have these block walls or these domain walls or Néel walls be actually quite wide. Now, this is actually quite important if you start thinking about polycrystalline material, crystalline magnets. So now we're talking about lots of little crystallites separated from each other of magnetic material. And if the size of the crystallite in number of atoms going across is less than this magic number, the size of the domain wall, then the whole atom, the whole crystallite has to have its magnetization pointing in just one direction. Has to point in only one direction. Each crystallite can point in a different direction, but each crystallite has to be pointed only in one direction. And the reason for this is because you don't have enough space within one crystallite to rotate the spin from one direction to another. It's too stiff. You can't, the coupling between neighbors is too strong in order to get the spins to rotate within one crystallite. And you might think that this 100 atoms is rather small, because each atom is only an angstrom or 2 angstroms or something. But if you have 100 atoms in this direction, 100 atoms in another direction, 100 atoms in another direction, all of a sudden you have a million atoms you're talking about. So these crystallites can actually have an awful lot of atoms in them, and you can still think of them as microscopic individual magnets pointing in just one direction. Okay? So far so good. I will resist the urge to make jokes about one direction. All right. Okay, so let's imagine that we take one of these crystallites and we are going to apply, so we have a crystallite here, and suppose it has an anisotropy axis in this ray, z hat, that it wants to point its magnetization either up or down, and let's, for the sake of argument, we'll put the magnetic field in that direction as well. The energy, and then the magnetic moment can be pointing in any direction we like. The energy of that crystallite is some E naught. There's going to be minus m dot b. And then there's the anisotropy energy, minus kappa mz squared, this, that wants the magnetization to point either directly up or directly down. So if we decide that, okay, so if the angle between M and B is theta, then we can rewrite this energy as E naught minus mb cosine theta minus kappa m squared cosine squared theta. And in fact, we might even let x equals cosine theta. And then what we have is a quadratic, E naught minus mb x minus kappa m squared x squared. And we can plot this thing. Oops, I'm running out of room, aren't I? Okay. We can plot this thing as a function of theta, or as a function of x. So this is the energy. And let's start in the case of B equals 0. So if you have your crystallite in zero magnetic field, and you have energy, over here is x equals minus 1, and over here is x equals plus 1. What we have here, so x equals minus 1 is theta equals pi, x equals plus 1 is theta equals 0. So this over here is the magnetization pointing down. And over here, we have the crystallite with the magnetization pointing up. And the energy is quadratic, looks kind of like this. So there's two stable points. The stable point here is to have the magnetization pointing down, and the stable point here is to have the magnetization pointing up. And it's much less happy to have the magnetization pointing in any other direction. This is not surprising because it's the anisotropy axis wants the magnetization point either up or down. Okay, now let's add a non-zero magnetic field. Okay, so now we'll let B not equal to 0, or B small, but not equal to 0. Not equal to 0. So now let's replot. Again, we have a parabola. It's still quadratic, but the parabola is now shifted because of the linear term in that in the energy. So that the peak of the parabola will not be in the center anymore. It will be off center. So we'll get a parabola that looks like this. And again, over here, what we have is magnetization pointing down, even though the magnetic field is pointing up. And here we have the magnetization pointing up and the magnetic field pointing up. So this point here, having the magnetization pointing in the same direction as the magnetic field, this is definitely the stable minimum. Whereas this point over here is metastable. In order to get from the metastable case of the magnetization pointing in the opposite direction as the magnetic field, in order to get down to here where it would rather be, it has to get over this activation barrier. And this means you have to take all of your atoms, maybe a million of these atoms, and somehow flip them all over simultaneously, either thermally or by a quantum tunneling. And that's a process that's so difficult that at low temperature it may never happen. So you can have these little crystals of magnet have their magnetization stuck in the wrong direction. Now let's turn up the magnetic field a little bit more. So now we have a large magnetic field, large B. Again, we have a parabola, but the maximum of the parabola has been shifted all the way off to the left. This is x equals minus 1. This is x equals plus 1. And the maximum of the parabola is way over here, off the plot. And so this point here, with the magnetization pointing in the opposite direction of the magnetic field, is now unstable. Whereas this point over here is the only stable point with the magnetization pointing the same direction as the magnetic field. Okay? So if the magnetic field is turned up enough, then you can flip over all of the magnetizations to point in the direction of the magnetic field. Is that clear how that works? Okay, so this is a picture you've seen before. It's a picture of a so-called hard ferromagnet. Maybe I should even write that word down because it's used often. Hard ferromagnet. Hard ferromagnet is when you actually have M not equal to 0 in B equals 0. And the way you get hard ferromagnets, we explained how you could get hard ferromagnets by pinning the domain walls, but you can also think about getting hard ferromagnets from having lots of little crystallites, and you need to, in order to push the crystallites to flip over, you have to give them some coercive field. You have to give them a finite magnetic field in the wrong direction, or in the opposite direction, to get them to all flip over. If you just give them a small magnetic field in the other direction, they don't flip over. And this is what gives these magnets hysteresis loops. Now, if you think about it for a second, you realize that this picture of pinning domain walls in a crystalline magnet, this picture, oops, where'd it go? This picture here, where the domain wall is stuck on its position because it has an energy activation barrier to get off of that, that position here where the atom gives it a lower energy if the domain wall goes to that point. It's extremely similar to what we have here with all these little crystallites. The only difference here is that you can think with the crystallites, the domain walls are always between the crystallites, if you want to think of it that way. That some crystallites will point in one direction, some crystallites will point in the other direction, and to move the domain wall, you have to flip over one more crystallite. So it's extremely similar physics. The moral of the story is that in order to get a real magnet, a hard ferromagnet, somehow or other you have to have disorder in your system, whether it's making the system into small little crystallites or putting disorder in that's going to pin the position of the domain walls. Okay, that's all for today. I will see you, is it Thursday? Thursday? Yeah, Thursday? Okay, have a good weekend.